Good morning and welcome to this next lecture on sound and structural vibration. Last time we had arrived at this integral, okay, from the paper by Majdanek. From here, Majdanek proceeds to approximate, as I said last time, the integral, this integral for various modes, okay, of this simply supported plate, okay, simply supported plate. And also in various frequency regimes. Okay, so there is the acoustic wave number K. There are the plate modal wave numbers kpx and kpy. So now and the free wave number of the panel, which is kp. So now various relations between them, whether k is greater than kpx, k may be greater than kpx but less than kpy, okay, and so forth. So all sorts of frequency regimes he examines and gives approximate formulas. Okay, so some are quite good and some not so good, but there are these formulas. Now, if you recall, I had spoken of the work by Wallace, okay, who does numerical calculations of modal radiation efficiency or radiation resistance, does not matter. So the picture looks like this. This is the non-dimensional modal coincidence gamma, okay, which is k over square root m pi by a whole squared plus n pi by b whole squared, and this is the value 1. So you get these sort of curves that approach 1 and briefly cross 1 and then asymptotically approach 1. Some other mode may behave like this, has a higher slope, okay, and some further higher slope with some oscillations that are related to this cells interacting with each other that I spoke of. Now it turns out that if you have odd modes, which are the most efficient in radiating, their slope at the lower end is 20 dB per decade. Okay, if you have odd even or even odd modes, it is about 40 dB per decade. Decade is 10 times increase in frequency. And then if they are even, it is 60 decibels, 60 dB per decade. Okay, that is because of further and further cancellations that happen at the starting point, which is the lower end of the frequency. Now, so these are numerical curves. These are numerical as I said. Now, you can superpose Majdanik's approximate formula on these modal radiation efficiency curves, and as I said, he does them in regimes. So you will have one curve here, a segment of a curve here, or a segment of a curve here, then there is a segment of a curve here, and there is another segment of a curve here, and so he approximates in this manner, and you can overplot on top of Wallace's numerical curves, and you have matches, and you have some places more inaccurate. The next portion which I will briefly touch upon is modal average radiation efficiency. Now, we saw how if we break up the wave number diagram into these regions of modes, where the node points are modes, then you have a acoustic wave number quarter circle, and then you have the free plate wave number quarter circle. So if we extend these boundaries in this manner, so you know these are, let me call them Y edge now. So you have a plate, which is X in this direction, Y in this direction, this has dimension A, dimension B. So these are Y edge modes. That means you have a strip on the Y edge that radiates here. These are Y edge. Then you have another set. You have these sort of modes where there is a strip along the X axis that radiates. So this strip radiates, the rest is cancelled. Those are these type of modes here, in this zone here. These are X edge radiators. And then you have corner radiators here and so forth. So let me show the corner radiators. The corner radiators look like this. Just a quarter cell radiates here. The rest is cancelled. So forth. Or corner. Now, if in reality if a plate is vibrating and radiating sound, it is not individual modes. Okay, several modes are vibrating, right? Several modes are present. Okay, so how to bring in this picture of several modes? Okay, so that means what, the KB circle is here, we are right here at a certain frequency, we are right here. Okay, so now if you look at the division here, let me use the blue line. If I draw this line over here, all these are X edge modes. All these are X edge modes. And all these, if I draw this line here, all these are Y edge modes. Similarly, these are corner modes. Similarly, these are corner modes. Okay, so you have on the KP circle, on this KP quarter circle, you have a number of Y edge modes, a number of corner modes, and a number of X edge modes. Okay, and to begin with, they are discrete. Okay, in actuality they are discrete, but the thing is that there are infinite dimensions of panels you could choose, so infinite ways that these nodes could land on this particular line, and there is no general way of presenting the picture of panel radiation. So what Majdanek did was that suppose there is a continuous presence of modes. Everywhere there is a mode, not discrete points. Okay, and suppose they carry the same amount of vibrational energy. Each of them carries the same amount of vibrational energy. So what is the average radiation resistance? At a certain frequency. Okay, so we are trying to find an average. Okay, so let me use another picture here. I have the acoustic quarter circle, and its bounds then the panel free wave number quarter circle. Okay, and if I draw this line here, if I draw this line here, you have along this red portion X edge modes, along this portion you have Y edge modes. Now a continuous distribution, we are going to make it a continuous distribution, and then along here you have corner modes. Below, full panel coincidence frequency. Okay, so now if I join this also, okay, so and I call this the A strip, I call this the B strip, call this the C strip. Okay, the A portion has X edge modes, so I will use the X edge mode approximate formula derived by Majdanek. and that will be made continuous. The variable, the modal variable will be made continuous. Okay. Then we have the B strip where we have corner modes. Okay. So there we will use the appropriate approximate formula. Then lastly we have C where you have Y edge modes. Y edge modes. Okay. So we will use the formulas from Majdanik's paper and we will make the discrete variable continuous, but we need a few special relations here. So we are going to measure theta in this direction. Increasing theta will be measured like this. Theta increases like this. Okay. And up till here we'll call it theta 1, and till here we'll call it theta 2. Okay. So now let us see some relations we have. So this radius is obviously Kp. This radius is Kp. Okay. This big radius is Kp. But this is K acoustic wave number, this is K the acoustic wave number, this is K the acoustic wave number, this is K the acoustic wave number. Okay. So now let us see sine of theta 1, sine of this angle here. Okay. So it should be a perpendicular by hypotenuse. So this perpendicular is K, hypotenuse is Kp. Okay. Next we have cos theta 2. Okay. So cos theta 2 is this angle. Okay. So what is that? That is base by hypotenuse. Base is what? K. Base is K. Hypotenuse is Kp. So that is also K over Kp. Okay. And we'll use a substitution which is Kp square minus K square is equal to mu square. Okay. And further sine square theta 1 is equal to K over Kp whole squared, which implies that 1 minus sine square theta 1 is equal to Kp square minus K square by Kp squared, okay, which implies that cos theta 1 is equal to mu over Kp. Okay. Similarly, we will have sine theta 2 is given by mu over Kp. Okay. So now if we summarize sine theta 1 is given by K over Kp, cos theta 1 is given by mu by Kp, tan of theta 1 is given by k over mu sec of theta 1 is given by kp by mu. Similarly, sin theta 2 is given by mu by kp, cos theta 2 is given by k over kp, tan theta 2 is given by mu over k, and cosec theta 2 is given by kp by mu. Okay. So now how is this average radiation efficiency resistance going to be computed? We'll go from 0 to theta 1. Okay. Are x mode x edge radiators d theta plus integral theta 1 to theta 2 the corner radiators d theta plus integral theta 2 to pi by 2 the y edge radiators. Okay, and then the whole thing is over pi by 2, so we will multiply by 2 by pi in the end. Multiply by 2 by pi in the end. Okay, so now let us see this the x edge radiators. Let us see the x edge radiators. The approximate formula by Majdanek is of this form: area of the panel rho A C K A by K P y whole squared divided by K A into H. H for him is A. H for him is B. Sorry, B. Is B. Y dimension. Okay. A, B. Then we have in the numerator 1 plus Kp square minus Ka squared by Kpy squared by Kp squared minus Ka squared by Kpy squared to the power 3 by 2. Okay. This is an approximate formula from that big formula that we derived last class. Okay. Now in here Ka is the acoustic wave number which is fixed at a frequency. Kp is the panel free wave number fixed at a frequency. The only varying thing is Kpy, the y component, okay, of Kp. It varies with theta. So Kp will be made a continuous variable as a function of theta. Okay. So let's see now what we do. Okay. So as a result, what will happen is that the formula will become Ap rho A C K A by H kpy squared into 1 plus mu squared by kp cos theta whole squared. Okay. So what is kpy? This is kp. Theta is measured like this. So this is kpy. Kpy is kp cos theta. Okay. And in the denominator we have mu cube and kp cube cos cube theta. Okay, and this is also kp square cos square theta. So as a result we will get, I am going to use b instead of h now, ap rho a ckA by b, the dimension in the y direction, into k square p square, kp square cos square theta plus mu square okay divided by kp cos theta into mu cube. So this becomes ap rho a ckA by b, okay, into kp cos theta by mu cube plus 1 by kp mu cos theta. Okay. So if we now integrate this, from 0 to theta 1, we integrate from 0 to theta 1. So what happens, we have ap rho a ckA by b kp by mu cube integral 0 to theta 1 cos theta d theta plus 1 by kp mu integral 0 to theta 1 1 by cos theta d theta. We are out of time, so I will close the lecture here and continue from the next class. Thank you.